And we can proceed with the next talk by Peter Dunn. We speak about a determination for the most accurate SLR stations.
Now, ITF 2020 allows us to exploit the property of SLR data to separate a range bias from a height displacement in a 7-day arc. The various systems that comprise the ILRS network contain several different species. Each of these species has a different characteristic error. The significant errors in the Mathis systems, which are based on the MCP microtunnel plate, essentially are dominated by discriminated time warp. The discriminated time warp turns out not to be an exact straight range bias. There's a certain range dependence associated with it. And so the ability of the SSEM technique used in ITO 2020 has difficulty separating that particular signal from height displacement. On the other hand, discriminated time warp does not produce a long-term effect, and so the Mathis systems do perform very well with the SSEM established compensation for the station positioning. Other systems, such as the CSPAD in Grants, suffer mostly from profile clipping characteristics when it comes to the features in the systems which are not well compensated by the SSEM technique used in ITO 2020. And Andrea has shown how the non-linearity in the Stanford counters at the Hurst-Massue system, the single photon system in Hurst-Massue, can produce a certain number of complications. However, common to each system are errors which are straight range biases, and those are very well accommodated by the SSEM technique used in ITO 2020. And this can be demonstrated by the fact that we can use the range bias estimates to help calibrate the systems. The range bias series are available on the JSET website, from which I've taken the following range bias time series. In this particular case, for the NASA station at Yarra-Gadi. And you see that there is a reasonably consistent positive range bias signal which jumps in about 2019 by approximately 6 millimeters. That is the jump which is considered in the ITO 2020 analysis to readjust the range bias. It turns out that a Minico test supporting the systems shows during that period a 6 millimeter separation between two targets, one of which is the prime target, which suggests that the prime target did actually move 6 millimeters. And the overdue survey for that site, we would anticipate would show it when we actually get the report. if we squeeze the scales around for those two systems, the vertical and horizontal scales are about the same right there. We can see that the displacement of the prime target B does correspond to the time when we see a jump in the range biases. And I think ILRS 2020 assumed a linear drift during that period, but I would personally think that the prime target probably moved 3 millimeters for 1 year or so, and another 3 millimeters the other year. So it's possible to actually interpret these biases in terms of real improved calibrations for the systems. ILRS 2020, with its publication, allows us to plot 2 stations at a time, as it turns out, for the particular arrangement published. And I show here the 2 stations at Graz and Hurstensue. They're about the same positions, and so you'll see that the horizontal components are very similar. The vertical components, which are shown on the bottom line, show the improvement in the height definition when Legos 2 is used in 1992. And both the bottom line on the main plot and the bottom lines on the thumbnails to the right show that each of those stations are showing pretty flat, long-term height behavior. You'll see in the very bottom right the little hiccup in 2002 that Andrea addressed in her last talk. If we look at 2 more stations available on the ILRS 2020 website for anybody to plot, you would find, comparing Goddard and Graz, this position. They're, of course, in totally different locations, so the horizontal components will be totally different. But the height components, you see, are very similar, except for the fact that Graz has got a relatively flat height behavior, whereas Goddard has got about a 2 millimeters a year subsidence. If we compare Goddard and Hurstensue, we see that the Goddard height rate is relatively consistently steady, a couple of millimeters a year, but Hurstensue is flat. And if we actually take a bird's eye view of the very accurate period since 2002, when Hurstensue had totally compensated all the straight range biases, you will see that Greenbelt is steadily subsiding at a couple of millimeters a year, but Hurstensue is not. One reason for that would be that the four-bulge collapse present at Hurstensue up until about the year 2000. After 2000, because of the rebound of Greenland after the ice melted, would be compensated by the vertical land motion associated with that Greenland ice melt, which would explain why Hurstensue in the very recent past would behave sort of different. So we have advanced from geodesy to geodynamics to the change, measuring the change in geodynamics at these stations with these very accurate systems and with the advances in laser data analysis. One thing that I might also add is that although Cinzia sort of described these range biases as nuisance parameters in the laser data analysis, I think it's quite possible that we can use this information to better calibrate our systems, and that would allow us to get even improved station positions and advances in the definition of the reference frame. Thank you.
Thank you.